In this video, we are going to be analyzing fluid flow through a pipe using this question. The question says, crude oil is transferred at a flow rate of 0.2 meter cube per second from one storage tank with a fluid level of 19.5 meter upslope to another storage tank with a fluid level of 30.5 meter above the first tank fluid level. If the pipe length is 800 meters and the pipe diameter is 457 millimeter, what is the flow velocity? Your given assumptions. Take dynamic viscosity as 1.848 by 10 to the power of minus 3 Pascal seconds. Your given density as 839.8 kilogram per meter cube. You're given pipe wall roughness epsilon to be equal to 0.05 millimeter. You're given efficiency as 85%. There are two angular bends with K bend, which is the coefficient of bend, equal to 0.6. There is one valve after the first tank with coefficient of valve equals 0.9. Second question says, what is the Reynolds number? Third question says, what is the relative roughness? The fourth question says, what is the frictional head loss? The fifth question says, what is the sum of the minor head loss? The sixth question says, what is the pump head loss? And the seventh question says, what is the pump power? Okay, so let's show a diagram to illustrate what the question is saying. Now you have two tanks. This is the first tank and this is the second tank. Okay, the first tank transfers crude oil up slope, okay, down to the second pipe. Now this is the level of the first pipe. Z1 was given as 19.5 meter. Now the level of crude in the second pipe was given as 30.5 meter. So this is the height of crude in this pipe. The first question is asking us to find the velocity of flow through the pipe. Now to do this, we simply employ Bernoulli's equation. What is the Bernoulli's equation? From Bernoulli's equation, the pressure head at the inlet P1 all over W plus the kinetic head at the inlet V1 squared all over 2G plus the potential head Z1 at the inlet is equal to the pressure head at the outlet. You have P2 all over W plus the kinetic head at the outlet V2 squared all over 2G plus the potential head at the outlet, which is Z2 plus all the losses. Okay, so plus losses. Now at the inlet there is no pressure head, which means this is taken as 0. Same thing as the outlet, there is no pressure head, also this is taken as 0. At the inlet there is no kinetic energy, so this is also taken as 0. At the outlet there is no kinetic energy, this is also taken as 0. But we have the inlet height and we have the outlet height. Therefore the equation remains now Z1 equals, over here we have Z2 plus all losses. Okay, so you can simply rewrite this equation by sending Z1 over here. It becomes Z1 minus Z2 equals all losses. Okay, so Z1 minus Z2 is called the potential head. This is the equation we are going to use to solve. Z1 minus Z2 is simply the potential head, which means difference in height. But mind you, the height cannot be negative. So we are going to be rearranging this equation a little bit to obtain Z2 minus Z1 because we can't have a negative potential head loss. So this simply implies Z2 minus Z1 is equal to losses. Now, what are the losses? Okay, call this equation 1, where Z2 minus Z1 can be found. Okay, Z2 minus Z1 is equal to the height difference. The height level in the second tank is 30.5 minus the height in the first tank is 19.5. So if you do this, you obtain Z2 minus Z1 to simply be 11 meters. So this is the potential head, 11 meters. So having found this, next is to find losses. Now, what are these losses? Let's simply use H losses, okay, to indicate it because they are measured in heads. Okay, let's use H losses to indicate head losses. Now, and these head losses include, let's go through the tank again. As the fluid flows into this pipe, we have head loss due to entrance. So we have the entrance head loss, call that HI, entrance head loss or inlet head loss into the pipe. Plus, now the fluid keep flowing through the pipe. There's a contact between the pipe wall and the fluid. That gives rise to what is called head loss due to friction. So we have plus head loss due to friction. Plus, again, there is a bend in the pipe. As can be seen, there's a sharp bend. Even in the equation, it was indicated that there are two angular bends with coefficient of bend. Okay, so we have bend in the pipe. So for that reason, we have head loss due to bend. Plus, again, it was also indicated in the question that there is a valve in the pipe. So therefore, we have head loss due to valve called that HV. Now, as the fluid flows up to this point, it now enters into this other tank. So we have what is called the head loss due to exit of the fluid into this tank. So plus head loss due to exit of fluid. All right, so these are all the losses we have. So we need to calculate these losses one after the other. So let's start with the first. Call this equation 2. When we find all these losses, we'll plug it back into equation 2. The first is entrance head loss. Okay, entrance head loss, which is H1. H1 can be found using the equation 0.5 V squared all over 2G. Okay, where G is gravity, which is 9.81 meters per second squared. Therefore, this is equal to 0.5. V is unknown, so keep it as V squared all over 2 times 9.81. Okay, this simply implies that inlet head loss is equal to 0.5 V squared all over 2 times 9.81 gives us 19.62. So let's simply obtain the inlet head loss. This is going to be 0.5 divided 19.62. That gives us 0.0255 V squared. So this is our inlet head loss. Keep it aside. The next thing in the equation is the head loss due to friction. Now, to calculate the head loss due to friction, we make use of the Daicy-Weisbach equation. Okay, so from Daicy-Weisbach equation, we have that the head loss due to friction is given as 4FL over D times V squared all over 2G, where F stands for the coefficient of friction or the friction factor, L stands for the length of the pipe, D is the diameter of the pipe, and again, G remains gravity. So this is equal to 4 times. So when given a value for the friction factor F, so which means we actually need to iterate, making initial guesses. Now, we also were not given Reynolds number because in the question we are also asked to find Reynolds number. And since we weren't given the Reynolds number, it means we can also use the Moody chart to obtain a value for the friction factor. Okay, so after iteration and upon initial guesses, we take the value of the friction factor F to be equal to 0.05. Okay, so we have here 4F, which is 4 times 0.05 multiplied by the length of the pipe, and the length of the pipe was given in the question as 800 meters, so multiply by 800 all over diameter of the pipe, and the diameter of the pipe was given also in the question as 457 millimeter, which is approximately 457 by 10 to the power of negative 3 multiplied by V squared all over 2G, which is 2 times 9.81. So we are going to be multiplying everything together. Head loss due to friction is now equal to, so let's multiply all through now. Everything at the numerator, 4 times 0.05 times 800 gives us 160 V squared all over. Let's obtain everything at the denominator. Everything at the denominator gives us approximately 8. Okay, so we divide now. 160 divided by 8. This implies that the head loss due to friction is equal to, let's obtain 160 divided by 8. That gives us approximately 20 v squared. Okay, so we have our head loss due to friction to be 20 v squared. Now again, mind you, the value of the friction factor was gotten by iteration. Okay, so that's upon initial guess, and we had 0.05. Okay, so this is the head loss due to friction. Let me pull back equation 2 again. So from equation 2, we'll find head loss due to friction. Next is to find the head loss due to the bend in the pipe. And it was stated in the question that there are two angular bends in the pipe. Okay, so for that reason, the head loss due to bend is going to be equal to, so head loss due to bend okay, HB is going to be equal to total number of bends is 2 times the coefficient of bend times v squared all over 2g. So head loss due to bend is equal to 2, which is total number of bends, times k, the coefficient of bend in the question was given as 0.6. So we have times 0.6 multiplies v squared all over 2 times 9.81. So this is equal to, let's obtain everything at the numerator. 2 times 0.6 gives us 1.2 v squared all over 2 times 9.81 gives us 19.62. So this implies that the head loss due to bend is equal to 1.2 divides 19.62. That gives us 0.06 v squared. So we have 0.06 v squared. Okay, so the head loss due to bend is simply 0.06 v squared. Now, having found the head loss due to bend, let's fall back to equation 2 again. The next is to find head loss due to valve. Okay, so in the question, we were given that there's a valve in the pipe. So we'll find the head loss due to valve. Now, the head loss due to valve HV is taken simply as the coefficient of valve times v squared all over 2g, and this is equal to coefficient of valve was given as 0.9. Okay, v squared all over 2 times 9.81. So this is 0.9 divide v squared divides 19.62. So this implies that the head loss due to valve is equal to, so let's obtain that division. That gives us approximately 0.05 v squared. So we have the head loss due to valve to be 0.05 v squared. Okay, finally from equation 2, we find the head loss due to exit of the fluid. Okay, so the head loss due to exit, head loss due to exit, HA is given as v squared all over 2g. So this simply implies head loss due to exit is v squared all over 2 times 9.81, which is v squared all over 19.62. So this implies head loss due to exit is equal to, that also gives us 0.05 v squared. So these are the head loss due to exit. Okay, so having found these head losses now, let's now compute our total head losses. Head losses is equal to, we said, the sum of the head loss due to the entrance. We said the entrance, we said the inlet head loss. So let's fall back here to the equation 2. So we said the inlet head loss plus the head loss due to friction plus the head loss due to bend plus the head loss due to valve plus the exit head loss. So the inlet head loss, we obtain the inlet head loss to be 0.0255 V squared. So you keep that aside. So we obtain the inlet head loss as 0.0255 V squared. We also obtain the head loss due to friction as 20 V squared. Then we obtain head loss due to bend as 0.06 V squared. Okay. Okay, now plus head loss due to valve, which is 0.05 V squared plus 0.05 V squared plus head loss due to exit of the pipe, which also give us 0.05 V squared. Okay, so it means total head loss equals, let's add them all up together now. This gives us 20.1855 V squared. So this is the total head loss. Okay, having found the total head loss, remember earlier we found that, okay, let me pull equation 1. Recall from equation 1, we said Z2 minus Z1 equals all the losses. So recall from equation 1, we said Z2 minus Z1 equals all the losses, and we obtain that change in height to be what? 11 meters. So this simply means 11 meters equals all the losses. Okay, so falling back now, we have that, okay, from equation 1, Z2 minus Z1 is 11 meters, and this is equal to 20.1855 V squared. So we can make V solid of the formula. This implies that V squared is equal to 11 divided 20.1855. This implies V squared is equal to, that gives us 0.5449. So we have approximately 0.5449. Okay, therefore we make V subject of the formula. This simply implies that V is equal to the square root of 0.5449, which implies, let's find the square root of that value. So the square root of that value gives us V. So this implies V is approximately 0.738 meters per second. So this is the value of V. Now the next question says we should find the Reynolds number. So to obtain Reynolds number RA is simply rho VD all over mu. So we know the rho, which is density. Density was given to us in the question, therefore Reynolds number is equal to. So in the question, okay, Reynolds number equals, density was given as 839.8, have 839.8 multiplied by velocity we just obtained as 0.738 multiplied by diameter of the pipe was given as 457 millimeter. 457 by 10 to the power of negative 3 all over viscosity was given in the question as 1.848 by 10 to the power of negative 3. So Reynolds number is equal to, let's obtain a multiple of the numerator. So everything at the numerator gives us 28326 approximately by 10 to the power of negative 3 all over 1.848 by 10 to the power of negative 3. Okay, so let's do this division. Upon division, we have the Reynolds number to be 153266, approximately 153266. So this is our Reynolds number. Okay, so Reynolds number is simply 153266. And this Reynolds number is greater than 4000. Reynolds number is greater than 4000. which means flow is turbulent. So this indicates turbulent flow. Alright, so since Reynolds number is greater than 4,000, it simply means that the flow is a turbulent flow. So that's that part of the question answered. The next part of the question says, what is the relative roughness? Now, the relative roughness is defined as the ratio of the pipe wall roughness divided by diameter of the pipe. And the pipe wall roughness was given to us, which is epsilon, was given simply as epsilon was given as 0.5 millimeter. So you have this to be 0.05, please. 0.05 millimeter, okay, which is 0.05 millimeter divided by diameter of the pipe was given as 457 millimeter. So this simply means relative roughness is equal to, let's obtain that ratio. That gives us approximately 0.00011, okay, 0.00011. So relative roughness is simply 0.00011. So in 3 decimal place, okay, in 3 decimal place, this is equivalent to 0.00, which you can still call 0.000, which you can still call 0, okay. So in 3 decimal place, you have 0.0000. So that's the value of the relative roughness. It is simply the ratio of the pipe wall roughness divided by diameter of the pipe. The next question says, what is the frictional head loss? Okay, we've already found this. Frictional head loss. The frictional head loss is found using Daicy-Weisbach equation. Okay, so frictional head loss, which is the head loss due to friction, okay, is what we found when we found the head loss due to friction. And the frictional head loss, let me pull it up. So we found the head loss due to friction as 20 V squared. Now we know the value of V. Let us plug into the equation. Okay, so the frictional head loss we had 20 V squared. Now we know the value of V. This implies head loss due to friction is 20 times V. V itself is 0.738 all squared. Therefore, let's obtain a value for the frictional head loss. That gives us approximately 10.893 in meters. So this is the value of the frictional head loss. The next question says, what is the sum of the minor head loss? Okay, minor head loss. Now the minor head loss are the other head losses excluding the head loss due to friction. The head loss due to friction is actually a major head loss. So minor head loss, H minor, is simply head loss due to inlet plus head loss due to bend plus head loss due to valve plus head loss due to exit. These are the minor head losses. So let's add their values up. Minor head loss is equal to head loss due to inlet. Let's obtain the value we got earlier for it. So earlier we got head loss due to inlet to be 0.0255 V squared. So keeping it down, 0.0255 V squared plus head loss due to bend, and we had the head loss due to bend as 0.06 V squared. So 0.06 V squared plus, and we had the head loss due to valve as 0.05 V squared, and the exit head loss we also had 0.05 V squared. Okay. So minor head loss equals, let's add all these values up. So that gives us 8.185, okay, 8.186 approximately V squared. Now we know the value of V squared, so this becomes 8.186 times V squared. V is 0.738 all squared. So this simply implies that the minor head loss is now equal to, that gives us approximately 74.2 meters. So this is the sum of the minor head loss, 74.2 meters. The next question says, what is the pump head loss? Now, the pump head loss call that H pump is equal to the potential head loss plus the total minor head loss, okay, plus the minor head loss. So the pump head loss equals potential head loss. Remember, we obtained that earlier, which is the difference in height of the fluid, which gave us 11 meters. That's 30.5 minus 29.5. That's the potential head loss, and we had it to be 11 plus the minor head loss here gave us 74.2. So this implies that the pump head loss is equal to, that gives us 85.2 meters. So this is the pump head loss. Now the final question says we should find the power, pump power. Okay, so to find the pump power, we simply make use of the equation density times the mass flow rate, which is a discharge, times gravity times the pump head loss. Okay, so pump power is equal to density, once more, was given to us in the question as 839.8 multiplied by discharge was given in the question. The mass flow rate was given as 0.2 meter cube per second in the question. So multiply 0.2 meter cube per second, okay, times gravity is 9.81 times the pump head loss, which we just found to be 85.2. So multiply by 85.2. This simply implies that the pump power is equal to, let's multiply everything together. So that gives us the pump power to be 140,382.98 in joules per second. So this is the value of the pump power. Alright guys, so that's it on that particular question on pipe flow analysis. I will see you in the next video with more questions on pipe flow. Thanks and cheers.